My name is Julie Gunkelman. I'm the Professional Development Coordinator for AMATYC. I would like to welcome you to the 2016 webinar series. And we have a special treat today. This is groundbreaking. We've never had a three-part webinar series. And so I think it is truly fitting today that Herb is the one who is giving this. His webinar series is entitled, If I Knew Then What I Know Now. And today's part is called, Have You Seen a Number? And it is our presenter today is Herb Gross. This presentation is sponsored by the Developmental Mathematics Committee of AMATYC. Our professional development core value is listed here. We have more information online if you do want to check out amatyc.org. Please note that the views expressed by the presenter are not necessarily the views of AMATYC. Commercial products mentioned by presenters are not endorsed by AMATYC. Our webinar series is sponsored by WebAssign. And because Herb is so well known, our founding president of AMATYC, we're going to choose to skip the biography today. I'm going to go ahead and put a link into the chat window in a little bit if you wanted to look at the history. If you go into the AMATYC website and go to the history, you're going to have a 70-minute conversation with Herb, and you can hear all about all the wonderful things that he has done in his career. I am now going to be pleased to turn this over to Herb, and you are on.
I'm on.
You are.
This is great. I'm very, very happy to be with you all today. Actually, at age 87, I'm pretty happy to be any place. And whenever I prepare a talk, whether it's a classroom lecture or whether it's a speech, keynote address, it's funny how the human mind works. I always flash back to the fall of 1954 when I was in my first year as a teaching assistant at MIT. And in those days, students wore shirts and ties to class. There was no such thing as cooperative learning. You weren't allowed to talk in class. And I'm lecturing, and all of a sudden I notice that one student is talking. I'm a very easygoing person, but being a first-year TA, I felt I had to implement the rules of MIT. And so I stopped my lecture, I looked at the student and I said, Tom, what are you doing? And completely flustered, I could see the red creeping up in his neck. He gave an answer that somehow my mind has never let me forget. He said, sir, I'm not doing anything. I'm listening to you. And it occurred to me that when you give a talk, and especially this kind of a presentation where it's a one-sided chat, and you'll be listening to me for the better part of an hour, it's very, very easy to start thinking of other things that maybe it's a waste of time. You see, I really have to connect. And this becomes very crucial because of a saying that's very, very prevalent in the hotel business and why they often have discounted rates on their rooms. The saying is that any room that doesn't get rented today never gets rented. And in the same sense, we can never have this hour back again. There's no way. In other words, if I were very wealthy and you didn't like spending the hour here, I could refund your money if you were paying for it. But if you say, give me back the time, except on Star Trek, we can't do that. So my hope is that we spend this hour in a way that you will all be pleased in the sense that it wasn't wasted and that it was a worthwhile way to spend the hour. Now, to give you the best perspective of how the Herb Gross love affair with the community colleges begins, we basically have to go back to April of 1958. It was in my 5th year of graduate studies at MIT when I received a call from Bill Perry, the founding president of Corning Community College, inviting me to be the founding department chair at the college. Now, the interesting thing is, it wasn't what Bill told me about the college. He basically had me at the name community college. You see, when you hear the word community college, you don't think of 2-year versus 4-year, public versus private, voc tech versus liberal arts. All you hear is a college that exists for the community. And that captivated me. In fact, I decided on the spot that I was going to accept that invitation, provided only that my wife didn't object. Everybody else did. In other words, they told me it wasn't a wise move to go from MIT to a community college, especially since community college wasn't a household word at that time. But here's what intrigued me. At that particular time, in the 1950s, only about 20% of a high school graduating class went on to college. That meant that the community college would be serving the 80% who weren't already going to college. In essence, I saw the community college as the Statue of Liberty for those who would otherwise have been academically disenfranchised. Not only that, but in an election year, the 80% outnumbers the 20% by a 4-to-1 margin. And I felt that it was crucial that we give as much education to as many people as possible. I was determined that the community college was not only different from the university, but it was equal to it. We share a partnership with the university in the development of any society. It's the university, places like MIT, that will determine the quality of life that a society enjoys. But how long that society survives to enjoy that great life depends on how well it treats the lower half of its population. And that's where the community college comes in. We are the ones that give people who otherwise might feel there was no real great hope for them the chance that there is hope. And if you think that we have a bad economy now, even as far back as when I retired from Bunker Hill Community College in 2003, there were already over 10 million community college graduates in the nation, probably 50 million more who had attended community colleges. Not everybody who attends a community college attends with the idea of graduating. And think of what the economy would be like now if the community college had not existed. It wasn't that these 10 million people said, should I go to Harvard or should I go to Bunker Hill Community College? We were the access that was necessary. So in my mind, I was seeing this as a very, very important thing. So I enjoyed teaching at the community college, and we now skip ahead to around 1966, maybe 1967, when we were at a state meeting, a community college get-together, where we're being addressed by a university professor from Cornell. And he talks about something called Math Zero, which is what the average student is expected to know. This was the CUPM. You remember that? The Committee on Undergraduate Programs in Mathematics. Math Zero is what everybody was supposed to know about math when they graduated from high school. And I raised my hand and I said, you know, sir, what you guys call Math Zero at Corning Community College, we call that Math 982. It was amazing how little the university realized the type of students we were getting. And that's when I felt it was time to form a statewide organization. And that's when NSMATIC, the New York State Math Association of two-year colleges, came into existence, to show people that we really were different in a good way from the university. And the problem was, I didn't really understand how we could make the public see that. Back in the early days of the community college, I could have students would tell me, my high school guidance counselor told me I wasn't ready to go to college, so they told me to come to the community college. That bothered me. We are a college. And what bothers me even more today is the number of states where they're taking the word community out of the title of community college, because it's something to be proud of. And so when I got the idea that we were going to form AMATYC, I knew that I had a message for the membership, but how could we brand ourselves? How could we pick a thing that would show the public that we were really different but equal to the university? My idea was that we would have to identify and solve a problem that the university had tried to solve but couldn't. And the thing that popped into my mind immediately was remediation. You see, the university has students who need remediation, but every one of those students, by default, has applied to and been accepted by a university. Most of our remedial students never applied to the university, and most of those who did weren't accepted. So that's what I felt would be our brand, that the nation would come to us when they needed help in remediation and mathematics, the same way as they go to MIT and Caltech when they need help in technology. I expected the universities to look up to us rather than for us to look up to them. Somehow or other, that never happened. And what occurred to me was what would have happened if AMATYC was founded after the internet was already well established. That's why I call the title of the series, If I Knew Then What I Know Now. If I were forming AMATYC now, my vision wouldn't have changed. All the things I've said about how I thought back in 1974, etc., they remain true. What's different is the implementation that I would have suggested might have been quite different. It reminds me of the kamikaze pilot, the only living kamikaze pilot. And they asked him, how can you be a kamikaze pilot and still be alive? He said, I love the concept, but I was far from enthralled with its implementation. And I think that's what happened, and one of the reasons that the new math back in the 1950s failed. I think it was epitomized by Morris Klein's pamphlet book called Why Johnny Can't Add. It was at a time when there were no computers, no calculators, and so the important thing was to get the right answer. It wasn't that important to understand why and when these formulas were needed. The important thing was that when you did a long division problem, you had to get the right answer. I often have pondered what would have happened had the new math been invented after the internet had been available. The first thing I would have done, once the internet was available, was to declare that the war on innumeracy was over and we had won it. A lot of people have looked at the calculator and the internet as sort of being, well, not a great ally of us, but it was the greatest. In other words, what difference does it make if you compute 3.14 times 2.7 using the calculator, or whether you compute it using an algorithm that you've learned by rote, where you multiply out, you count the number of digits, etc., and get the right answer. In other words, when people say using the calculator prevents you from thinking, keep in mind that using the long division algorithm by rote does the same thing. So I would have declared, look guys, let's tell the nation that the war on innumeracy is over, but we now have to fight a bigger battle. That bigger battle is called functional innumeracy. And I use that to parallel what we do with regard to language. Innumeracy corresponds to illiteracy. Illiteracy means you can't read, so innumeracy means you can't compute. Functional illiteracy means you can read, but you don't understand what you're reading. So functional innumeracy is you know how to compute, but you don't know when, where, and when to compute. This is epitomized by the students who say, it was an easy math course, I could do everything except the word problems. Sadly, in the textbook of life, there are only word problems. So let's go back to the problem of 3.14 times 2.7. I enter it into the calculator, and I get 8.478 for the answer. And by the way, I didn't just do that in my head. I worked out in advance, and I have a sheet in the back of the computer to remind me of what topics I want to talk about. Unfortunately, without my glasses, I can't see it very well, so I'm just guessing. But let's suppose that as you entered the 3.14, you hit the decimal point incorrectly. You omitted the decimal point. So instead of 3.14, you entered 314. And the calculator gives you this magnificent answer of 847.8. And I say, that's wrong. He said, can't be wrong. The computer told me that. Computers don't make mistakes. The people who punch the numbers in do. You see, what bothers me isn't that the person relied on the computer. It was that we should know enough number sense that 3.14 is less than 4, and 2.7 is less than 3, and 4 times 3 is less than 12. So the correct answer has to be less than 12. Now, there are lots of numbers that are less than 12, but 847.8 isn't one of them. You see, what we have to concentrate on now is let's take it as a given. That doesn't mean that we don't stress it a little bit or whatever it is, but let's concentrate more on making sure that the kids internalize and understand the why. I've had over 1 million views of my MIT calculus video series, and at least a third of them talk about they wish that more instructors had taught the why rather than just the how. In other words, if I don't know how to divide 1/2 by 1/3, if I have a what they call now smartphones, I just ask Siri, how much is 1/2 divided by 1/3? And I'll get a very sweet voice that gives me the answer right away. What it won't tell me is, was I supposed to divide 1/2 by 1/3? You know, if you want to see an example of that, just give a kid a problem like a man drives from town A to town B at 30 miles an hour, and because of construction, he only averages 20 miles an hour on the way back. What was his average for the round trip? Almost every student will say 25 miles an hour because 25 is halfway between 20 and 30. They don't understand, or they don't think about the fact that since the distance between A and B is the same as the distance between B to A, that at the slowest speed, you're traveling a longer time. And so the average would be closer to 20 miles an hour than to 30 miles an hour. We could go on and on that way. But the key that I found in my own mind was using numbers as adjectives that modify nouns. In other words, we do this in science all the time. We deal with quantities. We don't talk about 3. We talk about 3 feet, 3 miles, 3 inches. And what the 3 modifies depends on, when we talk about 3 inches is not the same as 3 feet. But the number 3, the adjective 3, means the same thing in both cases. There's that old story about the chef who used a little additive, a little horse meat, when he made rabbit stew. And they asked him, how much do you use of the rabbit and the horse? He says 50-50, 1 rabbit, 1 horse. You see, the 1 means the same thing in both cases. But the quantity, 1 rabbit, is not the same as the quantity, 1 horse. Now, you might ask, why is that so important? What difference does that really make? And the reason is that students in the average math course see numbers as, let me word it a different way. They see a world without nouns. It would be like a world, imagine living in a world with no nouns. Somebody says to you, what's that? And you say, it's a green. Person says, a green what? Say, what do you mean a green what? It's a green. Is green pretty? Well, green grass is pretty. Green mold on bread, not so pretty. In other words, the adjectives don't mean that much to us until we understand the noun that they modify. For example, students confuse a million and a billion. But if you have them modify seconds, a million seconds is less than 12 days. A billion seconds is more than 31 years. No one confuses 12 days with 31 years. And by the way, as adjectives, a million is always less than a billion. But ask your students sometime in what year they thought the millionth day since the birth of Jesus occurred. And have them look up in awe when they find out it hasn't happened yet and won't happen until the 28th century. In other words, a million as an adjective is always less than a billion as an adjective. But the quantity, a million days, is much greater than the quantity, a billion seconds. Little things like that that we can use. See, when you want to learn the tables, using numbers as adjectives that modify nouns, make the arithmetic much simpler. For example, to my knowledge, no one has ever learned the 19 table. But I can recite it very, very quickly. And how do I do that? I think of an example where I have 19 modifying a noun. I buy something for $19. How will I usually pay for it? Well, with a 20 and I get $1 change. In other words, 2 tens and I get 1 back. So to count by 19s, I simply add on 20 and subtract 1. 19 plus 20 is 39. Subtract 1, 38. 38 plus 20, 58. Subtract 1, 57. Kids can learn this way, and not only will they learn, they're so amazed by this because they haven't thought about it that way, that they actually will compare the results they got the new way with how they did it the rote memory way, and that will give them practice with drill. For example, most of my students only learn the tables through 9. When I was in school, we learned them through 12. Since I had all the students in class, I asked them how many knew the 13th table. And none of them said, we ever learned that. I said, but how do you do the 13th table? Just add a 10 and 3 ones. 13 and 10 is 23, and 3 is 26. 26 and 10 is 36, and 3 is 39. They get it. I say, okay, if you're counting by 13s, how far do you have to go before you get to 2,821? Now that's going to be, we make that into a practical problem by saying you have 2,821 books and you want to pack them into cartons of 13 books each. How many cartons are you going to need? Well, you know that every time you fill up a carton, you have 13 books left, but you got 2,821 books. Well, here's all the long division algorithm says is, when you say that 13 times 2 is 26, that's always true. But what the 26 modifies depends on what the 13 and the 2 modify. So for example, if 13 times 2 is 26, 13 times 2 apples is 26 apples, 13 times 2 people is 26 people, 13 times 200 is 2,600, and wow, right away you know that you need more than 200 cartons, because 13 times 200 is only 2,600. And you subtract that from 2,821, which is just a verbal way of going through the rote memory long division algorithm. It leaves you with 221 books still left to be accounted for, and you just keep continuing this process. I have my own website in conjunction with 2 people who will meet in our 3rd webinar, Rick Medeiros and Judy Bender. We have our own website designed primarily to help teachers in K through 12, but which you might enjoy looking at. The website, all one word, is www.mathasaSecondLanguage.org. And we'll go through this in much more depth so that you can really get a chance to see how this is done. The real thing that happens with this thing is when it comes to fractions. The average student has absolutely no concept of what a fraction really is. Oh, they learn mechanically how to add them, subtract them, excuse me, multiply them and divide them, but they don't really understand what a fraction is. There's an old joke about the man who was so happy with the clergyman and the church that he belonged to that as a reward, he increased his donation to the church from 1/10 of his salary to 1/20th of his salary. I tell that as a joke, but it happened in real life. Some of you may remember that wasn't that many years ago. A&W, the drive-in hamburger root beer joint, wanted to go in competition with McDonald's. McDonald's was offering a quarter pounder, so A&W thought they would offer a 1/3 of a pounder. And the amazing thing was nobody bought it, because they said, why should we pay more to get less? After all, if 3 is less than 4, 1/3 is less than 1/4. And by the way, McDonald's learned from that. They didn't come out with a half pounder. They came out with a double pounder. Notice the language, the marketing strategy. But this is how people think. Now, the interesting thing is that if we had enough nouns, we wouldn't need fractions. The reason that we need fractions is that when we write numbers in an arithmetic book, we don't write the numbers that they modify. For example, if I wrote in the nouns that they modify, if I wrote in the nouns that they modify, okay, I understand that 1 inch is not the same as 1 foot. But if I leave the nouns out, how do I know which noun the one is modifying? Can't modify both, you see. 12 doesn't equal 1 as adjectives, but 12 inches equals 1 foot. So if we had enough nouns, the problem would be very simple. And by the way, we invent enough nouns. We did, look, do we talk about 7/60ths of an hour, or do we talk about 7 minutes? It's funny, if I say 7/60ths, people say, oh my God, I can't do fractions. If I say 7 minutes, no one gets flustered. See, what is a minute? It's an abbreviation, a synonym for one of what it takes 60 of to make an hour. We don't talk about 1/24th of a day. We talk about 1 hour. What is an hour? One of the 24 that it takes to make a day. So we invent words like halves, thirds, fourths, fifths, just as we invent the words minutes, hours, seconds, etc. Just so that we have the vocabulary. What happens is when we write 3/4 as the fraction 3/4, no one sees the adjective noun theme there. For example, when you use the adjective noun theme, you have to be very, very careful, because since the nouns aren't there, when you write something as simple as 3 + 2 = 5, you have to say 3 + 2 = 5, provided 3, 2, and 5 are modifying the same noun. For example, 3 dimes + 2 nickels is equal to 40 cents, but 3 + 2 doesn't equal 40. So for example, if you were to write, suppose you spelled the word sevenths out. In other words, instead of writing 3/7, you wrote the adjective 3 and spelled out the word sevenths. And you say to the student, how much is 3/7 + 3/7? They see that the 3 and the 2 are both modifying sevenths, so they can add them. And so the answer is 5/7. Now write the problem as 3/7 + 2/7, and see how many students will write 5/14. They understand the concept. They don't understand the language. I was very confused with improper fractions when I was a kid. Why? Because 2/3 wasn't, they didn't tell me it was 2 of what it took 3 of to make the whole unit. They said 2/3 is you divide something into 3 parts, 3 pieces of equal size, and you take 2 of them. Well, that made sense to me. Now we came to 5/3, and they lost me. How do I divide something into 3 pieces and then take 5 of them? You do that, you can walk on water, I think. If they had said 5 of what it takes 3 of to make the whole unit, then very easily I could see, oh, I have enough to make a whole unit and have 2 pieces left over. It would give a whole new meaning in my mind to what it meant to divide, and you get a remainder. So you think things of this type. Now, one way that you can introduce this concept to people who are very, very much afraid of fractions even, is to ask a few questions that don't have any math intimidation to them. Ask them, for example, why, if teen means +10, why wasn't 11 called 1-teen? In other words, if teen means +10, why do we wait until after 12 before we introduce the new teen, the first teen? Why did we put 360 degrees in a circle when it would have been much easier to remember a number like 300? Or why do we put 5,280 feet in a mile when 5,000 would have been an easier number to remember? And the answer is, as far as the teens are concerned, until place value was invented, 10 was not an important number. What was important was to have a quantity that had many divisors. They put 12 in a dozen because more fractional parts of 12 were a whole number than fractional parts of 10. Think of how many divisors 360 degrees has. I mean, 360 is divisible by what? 2, 3, 4, 5, 6. If I was a physicist now, I'd say by induction it's divisible by everything. But it's divisible by almost everything. Tons and tons of divisors. So what that meant was that many fractional parts of a circle were a whole number of degrees. In a similar way, think of how many divisors there are of 5,280. It made many fractional parts of a mile a whole number of feet. So for example now, when I talk about a number like 2, but in the traditional way, ask a student, especially in remedial developmental math, which name's the greater number, 2/5 or 3/8. Many of them will pick 3/8 because the 3 is bigger than the 2 and the 8 is bigger than the 5. They don't see it as 2 of what it takes 5 of to make the whole unit versus 3 of what it takes 8 of to make the whole unit. Okay? So now what happens? Let's suppose we want to compare the size of 2/5 and 3/8. I'll just give you a general way of doing this that the kids find very easy. They think of a quantity. See, what does it mean when you say 2/5? It means 2 of what it takes 5 of to make the whole object. That means you want the unit that you're dealing with to be divisible by 5. What does 3/8 mean? 3 of what it takes 8 of. So you want the unit to be divisible by 8. Can we find a number that's divisible by both 5 and 8? Sure. Just multiply the two together. Won't always get the smallest one that way, but you'll always get a common multiple. That's a whole number operation, not an operation with fractions. Fractions are only involved in the definition. The arithmetic is all done with the adjectives. So for example, you say, okay, let's suppose that my unit is divided into 40 equal parts, 40 equal pieces. A fifth of that unit will be 8 pieces. So 2/5 will be 16 pieces. An eighth of the 40 pieces will divide the 40 by 8. That's 5. So 3/8 would be 15 pieces. So the 2/5 represents 16 pieces. The 3/8 represents 15 pieces. And since the 15 and 16 are modifying the same noun, namely pieces, 2/5 is greater than 3/8 by 1 piece. Now the problem with the word piece is that it's deceptive. In other words, if you divide something into 5 pieces versus 3 pieces, you still get pieces, but the pieces, when you divide it into 5 parts, are smaller than the pieces that when you divide it into 3 parts. So you have to make sure the pieces are the same size. Now, what happens is, I've never had a student yet that gets confused with that approach. What happens is, the danger comes in when instead of using the word piece, you use the word 40th. In other words, yeah, I can now add 2/5 and 3/8 because I'm adding 16 pieces and 15 pieces. The pieces all have the same size, so I add them as whole numbers. That comes out to 31 pieces. But this is like English as a second language type thing. If you want to learn a conversational language, the teacher asks you a question in the foreign language, and they expect an answer in the foreign language. In general, the beginning student does this in a multi-step way. They hear the question in the foreign language, silently translate it into their own language. Still silently, they answer it in their own language, and then they translate the answer from their own language into the language that they're studying. Okay? Bilingual means you leave out the middle 2 steps. In other words, you hear the question in the foreign language, you answer it in the foreign language. So I once had a Southeast Asian student who told me that she had a different way of determining when she was bilingual. And I asked her, what was it? She said, the first time I had a dream in English. And I had never thought about that before. If you're multi or just polylingual, what language do you tend to dream in? And I was going to make up a joke and say, I asked her what the dream was about, and she says, I don't know, it was in English. But the point I'm driving at is, the question was, how much is 2/5 plus 3/8? We found out that it was 31 pieces. The problem is, that was after we translated the problem from the math into visualizing it as pieces. I call it the cornbread. I use a thick number line, primarily because it's easy. You ever tried to divide a circle into 7 parts of equal size? But it's very easy with the number line because of Euclidean construction. It's very simple. And so I use what I call the cornbread model. It's actually a rectangle, which I personify by calling it a cornbread, and it's really a thick number line. And so basically what's happened is the student has been asked the question traditionally, has answered it in the language of cornbread, and now has to translate it back to the language in which the problem was given. And so instead of saying 31 pieces, it's what? 31 of what it took 40 of, and that's called 40ths. So the answer is 31 40ths. And from that point on, they learn the algorithms quite easily. And the biggest culprit in the study of fractions that I've found in remediation is not defining the word numerator and denominator correctly. It was very, very early in my teaching career in Corning, New York. It was probably 1959, possibly 1960. I was doing a workshop for elementary school teachers. And I talked about the top and bottom of a fraction. One of the teachers said, Professor Gross, how do we expect the students to use proper language if you're using improper language? Well, I often used improper language, but I didn't know what I had done wrong. I said, what did I do wrong? She said, you said top and bottom. I said, what should I have said? Oh, she said, numerator and denominator. I said, and what is the numerator? She said, the top. Well, it kind of startled me. After all, if top and numerator mean the same thing, say top. But they don't mean the same thing. For example, Christian Dior did not invent a numeratorless bathing suit. Think of the word numerator. It says much more than top. It suggests the word enumerate, which means to count. To count answers the question of how many. How many is an adjective. The numerator tells you how many. Denominator, denomination, the size. The top number tells you how many. The bottom number tells you the size of each piece, where you have to be careful. In other words, if the denominator is 5, the size of each piece isn't 5, it's 1/5. And so, for example, if you're given a problem that doesn't have, you're adding 2 fractions that don't have a common denominator, you find the common denominator the same way as you did when you asked, how much money is 3 dimes plus 2 nickels? You said, okay, a dime, we'll find the common denomination. A dime is 10 cents, so 3 dimes is 30 cents. A nickel is 5 cents, so 2 nickels is 10 cents. And 30 cents plus 10 cents is 40 cents. What you did was you found the common denomination. And it didn't have to be cents. It could have been nickels. You could have said, oh, there's 2 nickels to a dime, so 3 dimes is the same as 6 nickels, and 6 nickels plus 2 nickels is 8 nickels. Or you could have picked dimes. You could have said 2 nickels is a dime, so 3 dimes plus 2 nickels is 3 dimes plus 1 dime, which is 4 dimes. Now the numbers 40, 8, and 4, 40, not 48, 40, 8, and 4 are all different adjectives. But the quantities 40 cents, 8 nickels, and 5 dimes, 4 dimes all mean the same thing. And the kids really get that. And the reason I'm bringing this up is we are the ones who see the kids who have really fallen through the cracks. I think I mentioned that earlier in my presentation. But some of my university colleagues chide me by saying, Herb, we have remedial students too. but we don't have the problems you have. Well, they don't have the same remedial students. We are the ones who see the really remedial students. We are the ones that firsthand get to see what's bothering them. And the reason I'm going through this, I'm not even going into higher math. I'm going to end this when I get through talking about fractions. I'm not even going to mention mixed numbers, percents. I'm not going to mention how this stuff comes up in algebra and trigonometry. Like, why did we pick radians when we already have degrees? There are very, very nice reasons for this that make sense when we talk about quantities. It's that my sincere belief is that if a student enters middle school already afraid of fractions, there's little to any hope that we will get them to be able to go into any STEM-related program. You can revise algebra, and that will be part of most of our next presentation. You can revise it any way you want. But the kids who have been turned off by fractions are just going to memorize whatever they can, and if they're really lucky, they won't forget about it until after they pass the exams on it. I don't know if it was a nationally syndicated TV show or not. It was something called, Are You as Smart as the Average Fifth Grader? And they asked the adults questions that the average fifth grader answered correctly, and the adult couldn't. And so it came to the conclusion that the average fifth grader was smarter than the average adult. In my mind, what happened was the average fifth grader hadn't been away from school long enough to forget what he'd been taught. What that program should have been was a longitudinal study. Have the student answer questions in the fifth grade, and then 30 years later, whatever, when he's 40 years old, ask him the same questions again. You see, my definition of education is the part that's left after you've forgotten everything else you've been taught. And just ask yourself, how many students who are majoring in English literature are going to remember the quadratic formula once they're through with the traditional algebra course? These are serious things that we have to consider, and we are the ones who can tell the universities what they should be doing. If I was still at MIT, my concept of the lower half would be the lower half of the top 2% in the nation. You see, my norm would be MIT students. I would have no idea what was going on below that level. Almost any university professor of mathematics knows much more mathematics than I know, but they don't have the experience of seeing what's going on in the inner cities, what's going on in our community colleges. And by the way, I'm not bad-mouthing the community colleges. I'm not saying that we don't have very good students. I'm saying that our primary mission is to be that Statue of Liberty for the kids who would otherwise never have had a college education. That's who we are. Yeah, we have, in fact, if anything, our challenge is much greater today than it was in 1958 when I became the founding faculty math chair at Corning Community College. In those days, if you had a high school graduation, if you were a high school graduate and you didn't want to go to college, there were plenty of avenues open for you. And if you were from the upper class and had money, you didn't need the community college. You could have, colleges were affordable then. Now what's happened? The jobs that you used to be able to get with just a high school diploma no longer exist. The credential is now some proof of post-secondary education. And at the upper level, college tuition has become so expensive that many parents who, by the standards of 1958, would have had their children go to a private college, now say to the child, go to the community college for 2 years. And in fact, many high schools have a program with the community colleges where the student completes high school and the community college at the same time. And then you can spend the last 2 years at the private 4-year college, whatever. So this is where I'm coming from. It's not so much how we teach, it's that we have to come up with a model that works. And that model is based on functional innumeracy. So let me just go back a while to the discussion on fractions just to cover a few more things that way. 1/2 times 1/3. Okay? How was I taught that? Oh, yeah, it's logical, they told me. What could be more obvious? Just multiply the two numerators, multiply the two denominators. Great, I got 1/6 that way. Now I want to add 1/2 and 1/3. Now, what could be more natural? I'll just add the numerators and I'll add the denominators. And I get 2/5 and the teacher marks it wrong. Why was it logical that we could multiply across, but we couldn't add across? And if I don't run out of time, I'll show you the connection between that. Adding, in other words, you can add 1/2 and 1/3. I won't use the word add. You can combine 1/2 and 1/3 in a way that 2/5 will be the correct answer. It's called the weighted average of two numbers. But I'll come back to that if I have time. If I don't have time, it's on the website in one of the lectures I made for the teachers. Well, here's what bothered me as a student. I've been taught that when you multiply, the numbers get bigger. So I multiply 1/2 by 1/3, and I get 1/6, which is smaller than either of the two numbers I multiplied. That really confused me. Well, the teacher said, oh, you know what you can do? When you see the time sign, think of it as the word of. See, it's not 1/2 times 1/3, it's 1/2 of 1/3. Well, that made it easy for me to understand. In other words, if I take 1/3 of 6, I get 2. And if I now take half of the 2, I get 1. So I see that very easily. What I don't see is why they use the time sign if all they meant was of. If you're going to take 1/2 of 1/3, why not just write it that way? Why do you write 1/2 times 1/3? And try to visualize how you would do that on the number line. It's easy to do it in the of form, but not easy to do in the times form. Well, one of the interesting things when you're using numbers as adjectives that modify nouns, you can always view the product of two numbers as an area. In other words, if somebody says to me, how much is 1/2 times 1/3? I say, let me think about that. I have a rectangle whose base is 1/2 and whose height is 1/3. What I'm going to do is I'm going to take a unit 1-inch rectangle, square, a 1-inch square. I'm going to cut it in half vertically and in thirds horizontally. See, that's the advantage of the cornbread model. I have two dimensions in which to work rather than just one. See, so in other words, if I take a unit 1-inch square, divide it in half vertically, in thirds horizontally, I get 6 congruent rectangles, each of which has dimensions 1/2 inch by 1/3 of an inch. But because the 6 rectangles are congruent, they all have the same area, and there's 6 of them, each one is 1/6. The area of each one is 1/6 the area of the unit square. And so 1/2 times 1/3 is of 1/2 of a square inch times 1/3 of a square inch is, I'm getting giddy, 1/2 an inch times 1/3 of an inch, when viewed as a rectangle, gives you an area that's 1/6 of the area of the unit square. So it's 1/6 square inch. Now the way the of comes in is look at that same construction. When I divided it in half, see, I now had 2 pieces. What did I do next? When I divided it horizontally into 3 equal parts, I divided each of the 1/2 strips into thirds. So that same rectangle represented 1/2 of 1/3 of the entire rectangle. So, and kids can visualize that. When you say 2/3 divided by 5/7, you know how to, you can invert, you can multiply, they just don't understand exactly what it means. I had that problem when I first saw division by fractions. What was 6 divided by 1/2? Oh, remember that little, did you learn that ditty in your generation? Ours is not the reason why. just invert and multiply? Yeah, I could do that. It raised a lot of questions. In other words, if I was dividing 2/5 by 3/4, I could memorize that I invert the 3/4. But why couldn't I be more democratic and just invert both of them? Or why did I invert the one on the right? Why couldn't I have just inverted the one on the left? And primarily it's because people haven't been taught to understand the mathematical definition of division. A divided by B means the number by which B has to be multiplied by to give A as the product. In other words, it gives you the relative size. It's like the rear bumper sticker that says, I may be slow, but I'm still ahead of you. Okay? What 6 is, when you say 6 divided by a half, I invert the half, I get 2. Now I multiply, I get 12. How can 6 divided by a half equal 12? I'm supposed to be dividing. No, the question is, relative to 1/2, how big is 6? In other words, what must you multiply a half by to get 6 as the answer? Now, once you do it that way, it's not hard for students to see that it takes 12 halves, like $12 to make $6. So you can make up a very easy problem for the kids to see in terms of unit pricing. Suppose there's a very exclusive brand of cheese that costs $6 for a half a pound. Now, to find the cost, to find the cost per pound, you take the cost and divide the total cost and divide it by the total number of pounds. So if it was $6 for 3 pounds, 6 divided by 3 is 2, so you would get $2 per pound. Now what about 6 divided by a half? It's $6 now per half pound. Well, let's see what I can do now. If I know the price of a half pound, since it takes 2 half pounds to make 1 pound, I have to buy 2 half pounds. Each half pound costs $6, so I'm paying $6 twice. That's where the invert and multiply rule came from, that you can visualize it. Since I'm only getting half a pound, I have to multiply that by whatever will give me a full pound. In this case, the arithmetic was easy. If the fraction had been more complicated, say instead of 1/2, it had been 3/7, then you would have multiplied it by 7/3. Because when you multiply a fraction by its reciprocal, you get 1, and that would have given you the cost per pound. So you say, okay, I buy 2 half pounds at $6 each. So I multiply 2 times 6 to get 12, and the cost is $12 a pound. Now, I don't know exactly how much time we have left, but let me go back to that 20 miles per hour and 30 miles per hour, and I'll show you why 1/2 plus 1/3 can be 2/5. At 30 miles an hour, that's 1 mile every 2 minutes, isn't it? At 20 miles an hour, that's 1 mile every 3 minutes. For the round trip, you have to traverse each mile twice, once on the way up and once on the way back. Okay? I think I just lost the picture. Is everybody, let me just see. Yeah, I don't.
Did you lose us? We can see you.
Well, you can see me fine.
Yeah.
In fact, without my glasses, I can hardly see anything. But anyway, now, so you traverse each mile twice. One way, it takes you 2 minutes. The other way, it takes you 3 minutes. So you've traversed a total of 2 miles in 5 minutes. And 2 miles per 5 minutes comes out to 24 miles in 60 minutes. So in other words, no matter what the distance is between the 2 towns, if you go one way at 20 miles an hour, come back the other way at 30 miles an hour, okay, the average speed is going to be 24 miles per hour. It's called the weighted average. You see, it's sort of like if you're buying 2 different types of candy, and one kind is $2 a pound, and the other is $3 a pound. If you were to buy 1 pound of each, you're spending more money than if you had bought both pounds at $2. and less money if you had spent $3 for each of the objects. In other words, the very, very nice thing about mathematics is that when you explain the why, students doing a lot more. I used to have the students vote on whether they wanted 1/2 plus 1/3 to be 2/5, or whether they wanted it to be 5/6. They all picked 2/5. I picked 5/6. We had a democratic vote. They won 25-1. And in the Democratic Society, that was a landslide. I said, kids, you may regret this, but from now on, 1/2 plus 1/3 is 2/5. They cheer. I say, okay, now you work for me 30 minutes one day and 20 minutes the next day. How many minutes do you expect to get paid for? They said 50 minutes. I said, gee, that's what I wanted to pay you, but I don't want to break the law. They said, what do you mean? I said, I can only pay you for 24 minutes. They said, that's crazy. I said, no, it is crazy, but we passed the law. What law? Well, isn't 30 minutes a half hour? 20 minutes is a third of an hour? And we just said that when you add them up, it's 2/5 of an hour, and 2/5 of an hour is 24 minutes. Here's the important punchline to that problem. The kids, two things. The most obvious one is the kids will realize why you add fractions the way you do. The second one is even more important, especially for the kids who don't like math and science. The kids who are going to ignore math, but they're still going to be citizens, voters in a democracy. And they're going to realize that just because something passes by a landslide majority doesn't mean it was the right thing to do. And I think that's a lesson that every kid should learn, whether they're interested in math or not. Now, I don't know if I've come, at my age, I hate to say, have I come to the end of my time?
Yeah, we're counting on the top of the hour.
Okay, so are we about out of time now, huh?
We are. It's about 3:59.
Okay, so let me just tell everybody how much I enjoyed this monologue, and I hope that they enjoyed it as well. And feel free, see, we're going to have a session videoed where I will answer all of your questions, or at least try to. But in the meantime, if there's a burning question, a complaint, or anything, you are absolutely welcome to just email me at hgross3@comcast.net. Okay? And I only check my email about 3 times an hour.
Great. Thank you so much, Herb. This was absolutely wonderful. Lots of thought-provoking things going on. I'm sure you guys have questions. I didn't see anything go up in the question and answer box. There is a little bit of chatter going on right now in the chat box. I do have a few housekeeping things that I need to wrap up before we go today. And one of them is, let's see, thank you very much for participating today. Please look into joining AMATYC if you are not a member already. You can go to bit.ly, join AMATYC. The hot links no longer work in this platform, so we used to be able to just click on the link, and that won't work anymore. Check us out on Facebook. We are on social media. We are on Twitter as well. If you're going to look for recordings of this webinar or others, it's going to be at bit.ly, AMATYC-webinars. And it usually takes us about a week or two to produce and upload these webinars. It might be a little faster now that we have a different platform. If you need credit for being here today, you need to fill out our survey. It only takes a minute or two, and you're going to want to go to bit.ly/AMATYC51. I'm going to go ahead and put that in the chat window, and I'm going to stop recording. I can find that button. There we go.